Hello students, welcome to Classroom Point. In this session, we shall discuss the integrated rate equation for the first order reaction. Now, the name itself gives it is a first order. Order means it is the power of the concentration term, and first means that rate of reaction is directly proportional to the first power of the concentration term of the reactant molecule. Now, let us take a reaction. In that reaction, some reactant A converted to the products P. Now, for this initial concentration is at a time t equals to 0 seconds. Let the initial concentration of A is A moles per liter and P is 0 moles per liter. And after time t seconds, imagine the concentration out of the A moles per liter of the A, imagine X moles of the A converted to the product P. Then the remaining concentration of reactant is A minus X, and here the concentration of the product becomes X moles per liter. Now, according to the law of mass action, we know that a rate of any reaction is directly proportional to the concentration of the reactant. Here the reactant is A, so rate is directly proportional to the concentration of A. Since it is a first order reaction, it depends only on the first power of the rate equation. So rate is directly proportional to the concentration of A power 1. And rate can be written as with respect to the A minus d into concentration of A divided by dt is equals to, in the place of proportionality symbol, we can write some constant k into concentration of A power 1. This A power 1, 1 can be neglected because if you write or not writing, it is of no difference, so that we can remove in coming derivations. So this can be written as minus d into concentration of A divided by dt equals to k into concentration of A. Now, this particular equation we are deriving the concentration of A at a particular time t seconds. This is the t seconds. So at t seconds, so this A minus x we can write in this place. So it becomes now minus d into concentration of A divided by dt is equals to some constant k into A minus x. Now we can rearrange this equation as minus d into concentration of A by A minus x is equals to k into dt. Now let us try to do the integration of this equation. So on integrating the above equation on both sides, we shall get, now you can see here, minus of integration of d into concentration of A divided by A minus x is equals to integration of k, you can write outside, into dt. Now this particular form will give minus log A minus x equals to kt plus c. Let the equation be 1. Now we don't know the value of c, where c is the integration constant, where c equals to constant of integration. So our duty is to find out the value of c. Now at time t equals to 0 seconds, what must be the value of Ex? At time t equals to 0 seconds, x value is nothing but it is equals to 0, because there was no products. So x equals to 0. Now let us try to substitute both the t and the x values in the equation 1. Then we shall get minus log A minus 0 is equals to k into 0 plus c. Then it is equals to 0, and here we get the minus log A equals to c. This is the equation number 2. Now let us try to substitute equation 2 in equation 1. Then we can get the minus log A minus x equals to kt minus log A. Now write down the logarithms on the both sides, same on one side, so that we can get the kt equals to this minus log a becomes plus log a. So log a minus log a minus x we can get now. Now it becomes, it is in the form of log a minus log b, so its formula is log a by b. So we get the kt is equals to log a divided by a minus x. Now here logarithm is in the base c logarithm. If you want to if you would like to convert this base c logarithm into the base 10 logarithm, then this form is to be multiplied with the 10. And in meantime, let us try to send this t also this side, so we can get the form. Here we can write k equals to 1 by t into log a divided by a minus x. Now let's try to convert this base e logarithm into base 10 logarithm. That is k equals to means to for that conversion we need to multiply the equation that right hand side with 2.303. So k equals to 2.303 divided by t into log a divided by a minus x. This is the integrated rate constant derivation for the first order reaction. Now here we need to discuss, because various textbooks are giving various type of the terms in this particular area. So let's try to discuss that particular part also. So here, first of all, this A, what does it mean by A? A is nothing but the initial concentration. This the IC means initial concentration of the reactant, and A minus X is the final concentration of the reactant. So they are just terms. These you don't need to by heart every time. Initial concentration of the reactant divided by final concentration of the reactant. Some textbooks, instead of the A, they used to take the concentration of A as A naught. Then here they take the final concentration of the A as concentration of A, like this. Then in such case the equation becomes K equals to 2.303 divided by T into log concentration of A naught divided by concentration of A. And in some textbooks they used to take concentration of R naught. Initial concentration as the R naught, because R represents the reactant. There they take the R gives P, not A gives P. And here the final concentration of the reactant to be taken as like this. Then the same reaction becomes A equals to 2.303 divided by T into log concentration of R naught divided by concentration of the R. In another textbook, they take the initial concentration as C and the final concentration as CT. T means concentration at a time T. This one they take as either C or C naught. That is up to you, or up to that particular textbook person. So it is equals to K equals to 2.303 divided by T into log C naught divided by CT. So whatever it may be, meaning is same, only forms are different. The notations what we are using is different. It all depends on the convenience of the person. So you can take the a by a minus x, or a naught by a, or r naught by r, or c naught by ct. This is the integrated rate equation for the first order rate constant. Hope you all understood this particular derivation. Now let us try to see how the same equation, this equation I'll take this equation, how to write down in the exponential form. You can take either this one or this one or this one, any one. Only the thing is, wherever a naught is there, you can substitute r naught, c naught. Wherever a I'm going to write concentration of a, there you can write a capital concentration of r, or ct, or a minus x. Means I'm just taking only one particular form for the writing of the exponential forms. Now let us see the exponential forms. Now let us try to write down the exponential form of the first order rate equation. Earlier I have taken k equals to 2.303 divided by t into log concentration of A naught divided by concentration of A. So the same one we will rewrite in the form of exponential form. You send this t that side and convert the base 10 log into the base e logarithm. So we'll get the kt equals to log concentration of A naught divided by concentration of A. Now you send the logarithm that side, base e logarithm. So it becomes concentration of A naught divided by concentration of A equals to e power kt, and this is the exponential form, and this can be rewritten as concentration of a naught equals to concentration of a into e power kt. This is one form from this particular above equation. Or else, if you write this particular form in the reverse form, that means concentration of a divided by concentration of a naught, then here you will get the minus, so e power minus kt. Then in such cases, concentration of A equals to concentration of A naught into e power minus kt. So hope you understood the derivation of the first order rate equation and the exponential form. If you like it, please do not forget to subscribe the channel, as well as do not forget to comment on the about the channel in the comment box, so that it will improve our quality. So do not forget to subscribe. Thank you.